some of the previous topics we've been showing, we invite you to go to our website. There's some great material there. Our format for the day is that our speaker, Natasha, will speak for about 35 minutes or so, maybe 40, and then that leaves plenty of time for questions and answers. And we aim to finish by about 5 o'clock, no later than 5:15 definitely, but around 5 o'clock. If we don't want to do questions and answers, which of course we do, we use a program called Slido, an app called Slido. It's S-L-I-D-O. We emailed you a link to it this morning, but just in case, go to www.slido.com, or indeed you go to the App Store and download Slido. It's a good thing to have. It's commonly used in conferences. And you use the event code 2164. There's already a question up on that app, on that Slido event code from me. So what you do is you submit a question, and then you can also like other people's questions, and that gives me an idea of what people are asking and what people think is a question for me to ask. I'll facilitate the question and answer based on the question submitted, and I've always found it much easier to put the Slido on your phone and watch the presentation on the computer. So I recommend you go to Slido now, or as we get closer to Q&A, I'll remind you again. Now I'd like to introduce our speaker, Natasha. Dr. Natasha Hurley-Walker is a senior lecturer at Curtin's Institute of Radio Astronomy. She uses novel radio telescopes to explore the universe at some of the longest wavelengths of light. She sounds like she has a really cool job because she's discovered some amazing things. Her work has revealed the radio glow of the Milky Way galaxy, ancient cosmic explosions, plus hundreds of thousands of distant galaxies observed across such a wide range of frequencies that the unique spectrum of every object can be used to understand its underlying physics. I mean, just imagine your work day. What did you do today? Oh, I discovered a few galaxies. And wouldn't that be fantastic? So I think Natasha probably has a pretty good job, and it's really going to be great to hear what she's got to say. She's been publicly recognised for her science, her work in gender equity and in outreach activities. And indeed, she was named a WA Tall Poppy Scientist of the Year in 2017, an ABC Top 5 Scientist in 2018, and a superstar of STEM, Science, Technology, Engineering, Maths, in 2019-2020. We have actually had a couple of people from physics and astronomy do Curtin in the past. I remember Igor Bray and Roberto Soria on different occasions, and also David Blair from UWA. So they've always got something interesting to say, and it's not just the straight science, but other aspects too. I was going to say they give us a bigger picture, but hey, astronomy is so big already. I don't know if I can get much bigger, but hey, well, let's listen to what Natasha's got to say, and hopefully we'll learn a lot more, not just about the sort of work they do, but also the environmental aspects of what they do, and that'll be terrific. So Natasha, thank you again for volunteering to do Curtin Corner, and I'm going to hand it over to you.
Great. Thanks a lot, John. Thanks for having me. And thanks everybody who's come to hear me speak today. Yeah, so indeed, I'm a radio astronomer. I'm stood here, not here, unfortunately. This is a featureless white wall. But the image that you see is me at the Murchison Radio Astronomy Observatory, right next to 1% of a radio telescope that I've spent the last 8 years working on, called the Murchison Wide Field Array, which is a low frequency radio telescope. Looks a little bit different from telescopes you might think of, like Parkes radio telescope in the movie The Dish, or the VLA, which is in the movie Contact, although I am doing my best Jodie Foster impression. It's a low frequency telescope, and it's a precursor to the Square Kilometre Array, which will be one of the world's largest radio telescope, and I'm hoping eventually I get to work on that. But indeed, this talk today is on a slightly different topic. So I'm going to talk a little bit about my journey through some of the kind of cosmic perspective that astrophysics has given me. And then what I see as one of the most important challenges that we have facing us as a species today. And then at the end, what astronomers specifically are going to do about it. So hence the title, How to Explore the Universe Without Costing the Earth. So thanks for joining me on today's journey. So to recap just a little bit about why I thought this talk was important and how I've kind of got to this point. I've always been interested in space. As a little kid, always looked at astronauts launching and rockets taking off and thought how wonderful it would be to travel out there and explore the universe. And obviously having been able to move to the southern hemisphere and see our gorgeous night sky with the galaxy spread out overhead and the planets dotting along the ecliptic, it's just been a beautiful journey of discovery. And I've got to use my radio telescope and build an enormous, beautiful picture of the sky in the radio. And if you go online and you search my name, you'll find a TED Talk and you'll find my website and so forth. And you can see me talk all about this image, which is very, very beautiful. But basically, what I'm trying to get to is I've really appreciated how incredibly vast and gorgeous the universe is. But at the same time, to all of our instruments, it does appear to be somewhat empty. Now, we are looking, there are SETI programs, there are different groups of radio astronomers and other astronomers who look for signs of life on other planets. But at least as far as we can tell, at least within our little cosmic volume, our little bubble of our own galaxy, we're quite unique. We seem to be the only area where intelligent life is going about transforming the environment around it. And it's this kind of realization that we are a very, 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 very small place, one little Earth planet in a huge galaxy among hundreds of billions, possibly trillions, possibly an infinite number of galaxies, which makes me realize how special we are. And I think Carl Sagan put this best when he looked at the image that Voyager sent back of the Earth as Voyager exited the solar system. He said, "That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human who ever was lived out their lives on a mote of dust suspended in a sunbeam." So we really are on an extraordinarily small slice of the universe, and yet we have around us an incredibly complex and beautiful planet. So I think it's important that we look after it. So this is the astronomical perspective, or at least my astronomical perspective, use my own, on what I think is the biggest challenge of the 21st century. And I must forewarn you, I'm a physicist. We do have a terrible reputation for taking other people's fields and boiling it down into something incredibly oversimplified, coming up with a model, applying the model, and then saying, aha, aren't we clever physicists? When in fact, we've tremendously oversimplified things. So I would love to talk to, some of you, hear from you in the Q&A, be proved wrong, always good. But I'm going to try and stick to purely physical arguments that kind of work on large scales. So that'll become clearer as I go through the talk. So here's the classic physics starter. Assume a spherical car of uniform density. Everything here is going to be quite broad brush, and I'm sure there are many complexities that I'm omitting. Now, of course, what is the biggest challenge? What do I think is the biggest challenge? Well, I wouldn't be surprised if you agree with me that probably the ever-rising temperatures that we're experiencing and the prospect of human-induced anthropogenic climate change is pretty much the biggest challenge. Now, I would argue this is actually really a symptom of a larger challenge, but it's the most clear and present danger that we have and the most clear and present thing that we need to address. And I won't torture you with images of the bushfires from earlier this year, the bubbling methane clathrates that are coming out of the Arctic Ocean, the persistent droughts that different parts of the world have experienced, and we've already started to see the movements of climate refugees. I'll just focus on some of the positive things that we're starting to see, which is that people are paying attention. So, the Fridays for Future protests, spearheaded by Greta Thunberg, have been immensely successful in bringing the issue, and it seems that a lot of young people would like to have a habitable planet. The UN has endorsed taking action on combating climate change as goal 13 of its Sustainable Development Goals, which I'll get to more in a minute. And even left-wing, crazy socialist people like the International Monetary Fund, known for its very socialist policies, obviously being sarcastic, have actually mentioned that this is something that worth doing. It would be good to have a livable planet. Actually does impact the markets. So this is an important issue for increasingly large sections of humanity, and it's something that we should do something about. So here's the UN Sustainable Development Goals. It's one issue among, as they say, about 17. And of course, it affects everything else. So this is a report that just came out about looking at those sustainable development goals and looking at how possibly we can even understand and sort of use what we've learned in COVID to meet that sustainable development goal of combating climate change. So this is a graph of carbon emissions of our society over the last 20 years. And we have come up to the COVID breakpoint, where obviously international air travel has been shut down and a lot of carbon intensive events have not been able to take place. And you've plotted along the right hand side of the extrapolations, the trajectories. And so they're saying, well, look, we've brought down air travel. Perhaps we could learn from that optimistic scenario. We can actually cut our carbon emissions, and we can keep coming up with innovative practices that replace our carbon intensive ways of life. This is very positive. This must have taken them a few months of very fast writing to turn this around during the pandemic. And indeed, this graph shows the cost of energy over time. Indeed, the transition to renewables would be very straightforward. We should be doing this while we can, right? The graph here is showing the cost over time. Solar's come right down, and the dashed line is if you take into account the cost of doing something about climate change when you look at the fossil fuels. So we're quite below that curve, and we should be doing something about it. But this is where things start to get complicated. So let's address climate change. We can do that with wholesale transition to renewables, because electricity is something like 80% of our climate footprint. And great, 2 out of 17. I'm sure we can crack on with the others after lunch. It'll be great. But this is where my physics hat starts to kind of worry me. This is where I get this kind of alarmist vibe, which is in this bit about decent work and economic growth. Now, the first part I highly agree with. Decent work, we should all have decent working conditions. But it's the economic growth bit which I think may sort of contradict some of these other policies, particularly tackling climate change. So we all know economic growth, it's a good thing. It's what's fostered the last 500 years of immense development. And the idea is that, as things get better, you can invest, you have that certainty that things will get better, new technologies, and you go round and round and round, and it's a beautiful spiral. Rising tide lifts all boats. And indeed, if you look at our World and Data is a wonderful website. You can grab all sorts of fantastic data. If you look for the last 2,000 years of economic growth, it's obviously completely ramped up tremendously, such that it doesn't really even fit on the plot just in the last 100, 200 years or so. And we can squeeze that down by making it a log plot, but still the ramp in the last few hundred years has been absolutely absurd. So if we just focus on one of the countries here, if we just look at the United States and we look at that GDP, which is, classically used to measure economic growth. This is per capita, just because it makes all the numbers a bit easier. It's a nice straight line in log space. So what that means is it's growing at a consistent fractional percentage every year. It works out to be about 4%. So the economy is getting about 4% larger every year. Okay, this is reasonable. And I think if you asked random people, if I asked you guys, how much economic growth should an economy have, we'd all come up with some number between 1% and 10% as being a nice number that leads to more jobs. And anything less than 1% is a recession, and we don't really want that. Anything more than 10%, and you sort of think, oh, how do you deal with the resulting social changes? So that's a good number, right? Something we're used to. Now, if you look at the total energy use of the United States over that time, and you plot it again in a log scale, you get a really nice straight line as well. It's actually astonishing. I mean, correlation isn't causation, but this is causation. So it's going up in a straight line. This is obviously corresponding to the unlocking of more and more different fossil fuel sources. And you see kind of in the last 30 years, it's just slightly flattened a little bit, which mostly corresponds to the shift of manufacturing jobs overseas from the US, and so a rise in sort of services work. So let's take that as like a good economy, right? With 2.3% growth. You have to grow your energy use to grow your economy. And I'll come back to why you can't just decouple those things in a bit. So you need to grow your energy use 2.3% every year. And we've already established that we need to transition away from fossil fuels immediately and possibly start some kind of carbon capture because climate change is bad. So you need to grow your renewables footprint pretty quickly. So here is the broad brush picture of how you do that. Okay, we've got power along the y-axis. This is our net energy output of our civilization. And we've got the time from now into the future. And I mean, astronomically, this is a very short time. It's not the sort of time scale I'm used to dealing with. I'm used to dealing with at least 20,000 years for a star exploding, millions of years for dealing with radio galaxies, billions of years for dealing with cosmology. But hey, you know, meeting you guys in the middle. So we've got to just consider the next few thousand years. I know it's not much. So if we need to keep growing our energy use at about 2.3%, and if we need to fully transition to renewables, the amount of solar power you need to lay down is problematic. So within about 300 years, you need to cover an area the size of America in solar panels, which is tricky because we don't have that land lying around anywhere conveniently that anybody could use. And, you know, economic growth being what it is, where you say, well, we need to keep growing, you very quickly need to lay the entire Earth covered in solar panels, which is also somewhat problematic. There are people living there, food grown there, and so forth. And logarithmic, having exponential growth being what it is, you pretty quickly need to use the whole Earth, which just good luck. That's a lot of ocean to put solar panels on. Where do you even put the things that you're now using the solar energy for? So this is a problem. And then, of course, if we go even further out, it's just 1,000 years from today before we need to build the Dyson sphere, which is what you do to completely use all of the energy from a sun. And I actually did a fun calculation on this. If you disassemble the entire solar system, except for the sun, you can make a meter-thick Dyson sphere at the Earth's orbit. And that would be pretty cool. It's not going to happen, guys, dismantling Jupiter in the next 1,000 years. I know Elon Musk is very optimistic, but that's beyond us. And what really hits us, this is where 2.3% or any amount of economic growth really gets ridiculous, is in just another 1,000 years, you need to take over the galaxy. Now, I'm a physicist, and I know things are just theories, but the speed of light is not something we can actually exceed. And our galaxy is about 30,000 light years across. So no matter what you do, no matter what kind of engine you invent, you cannot cross the galaxy in 1,000 years, let alone take every single sun and cover it in a Dyson sphere in 1,000 years. This is completely physically nonsense. So I find this very entertaining because it's obviously an argument of reductio ad absurdum. We clearly aren't going to do any of these things. We're not going to cover North America in solar panel. We're not going to build a Dyson sphere in 1,000 years. I mean, who knows, maybe 1 million, but not 1,000. But that's the point. I'm not saying that these things are really silly and we should aim to do them. I'm saying that something is going to stop us from getting to this point, and you either need to decouple your energetic growth from your economic growth, like immediately, or you need to accept that at some point we're not going to be able to keep growing at around 2 or 3%. Okay? The two things something's got to give, basically. So let's ignore the astronomical solar system, going out and building a Dyson sphere. Let's just focus on the now. This is again where physics is coming in. If you are taking that much energy and using it to power your human civilization, energy isn't just, it's neither created nor destroyed. It starts as like something that is highly concentrated or useful. And at the end of whatever process that you have powered using that energy, it has become heat. It's become thermal energy, like long wave infrared. So, examples include you switch your lights on, the light comes out, it bounces off all the surfaces, and eventually it gets absorbed and then re-radiated as heat. And once it's heat, it's not very useful. You can't really do much with heat. Another example would be you have a hydro dam, the water comes down, it turns the turbine. You use that turbine to produce electricity. You send the electricity all around, people use it. The water's now at the bottom of the river, and you can't use all the heat from everybody's light bulbs to put the water back up again. You need like a concentrated energy source like the sun. So you end up with all this heat, and heat can be trapped by our atmosphere. It doesn't just radiate freely. This is kind of the problem with climate change, is we're increasing the layer of amount of CO2, which acts as a blanket and traps more heat. But if you just dump more heat into the system, that's also a problem. And what we're effectively saying with this energy growth argument is that we will just keep putting more and more heat into the system. As long as you're consuming the energy in whatever form, if you're consuming it on Earth, the heat is generated and has to go somewhere. So if you go with building a society that keeps growing energetically, in about 350 years, forget climate change and a, up to 5-degree global climate increase, you've got a 37-degree climate increase. And of course, by about 1,000 years, the Earth's surface is the temperature of the sun. Again, this isn't actually going to happen. I'm saying that sometime in the next couple of 100 years, we will be forced to use less energy or stop growing economically or decouple the two completely, okay? So let's talk about decoupling, because, that would be fun, right? So decoupling economic growth from energy use means that you're still growing, for instance, your services sector, your arts sector, but people are doing more fun stuff with less energy. So for instance, instead of going on a cruise ship and using all of that, oil that's been pumped out the ground to like move a huge ship all over the Earth and people taking photos and stuff, you could just wear some VR goggles and make brum brum noises and watch a projection of the Earth going by and, whales jumping and things. You could just stay where you are and experience that. I mean, I don't believe that that's a real substitute, but that's a thing you could do. Everything is like this, right? You could replace your conferences with remote work, and I'll talk about that more in a bit. All the way down to things like food. You got to eat. It could be in algae farms. It could be very efficient, but you've still got to eat. So you can decouple up to a point, but as long as we remain humans, we are still going to want to eat, probably use some kind of transport to go somewhere. And I personally don't want to live in a trailer doing nothing but looking at VR all day. So we can do a kind of toy model where we say we're really going to insist on this economic growth. It's got to happen. That's that black line where you have like an arbitrary economic scale, time along the x-axis. So the economy is going to keep growing. That's what's going to happen. And the green energy curve is what we need to taper off our energy. Okay, so it's going to have to stop growing or we cook the Earth. And maybe we can get some efficiency gains, which is what the blue curve is. It's not really important. But basically your energy stops growing, your economy keeps growing. And so then you can look at the resulting red points, and this is the percentage of your economy that exists in forms that don't use energy. So a CD of a festival that you went to, and perhaps you just watch that on repeat rather than performing the new festival, or the VR goggles, or so forth. And of course it just gets ridiculous, and at some point you can't replace any more activities. Everybody is using as little energy as they possibly can, but you cannot keep growing your economy without using more energy. So while substitutions and efficiency can help, and we certainly shouldn't ignore them, we come back down to the fundamental problem. doesn't buy us very much. So 11 years before I was born, another group of people, much better equipped than me, ecologists, economists, they produced a way better modeling system to deal with this kind of thing. All of my arguments so far have been purely energetic, but limits to growth, they made a very nice sort of feedback world system. And I only became aware of the existence of this book maybe 5 or 6 years ago. And I realized, this has all been done before. So I'm sure people have been paying attention, right? So they're a complicated model. You can see some of the outputs of that model along the bottom here. So there's a sort of population graph where you have things like the birth rate and the death rate and the resulting effect that has on the population, which is the red curve. There's the environment. So what resources we have left to exploit, the pollution we produce by exploiting those resources, and the economy. So we're generating food, we are generating services, and we're generating industry. So the graphs here are, the solid lines are what they knew about in 1972 when this book was produced, and the dashed lines show their model predictions. So to kind of give perspective, they wrote this stuff when people were landing on the moon, and we are just in widespread industrial agriculture had really swept the world in the Green Revolution. That's the kind of era. So how are we doing? It's been a while. Well, all of the solid lines are updates to this model that they produced. And, some things are really heartening, like our birth rate has come down, possibly due to better education and the availability of contraception in developing countries. Women's rights, some really great stuff here. So and the death rate has come down. Modern medicine is brilliant. Those two things kind of cancel out, so our population basically follows the same curve. We're using up resources at approximately the rate that they predicted, but nicely the pollution isn't quite as bad as they predicted, so that's nice. And all of the economy stuff that you can then get from that model sort of all looks reasonable. Now the big question, of course, is whether you then believe any of the inflection points in these curves. And, I'm not an ecologist, I'm not an economist, but I do worry about the excellent correspondence that they've, generated so far. And so we're at the situation now where space race is going on and climate change is clearly happening. Australian bushfires I've just got a pretty sad image at the top right. Prognosticating again about the future is really, really hard, but whatever could happen is going to happen. You could plot whatever happens on these graphs. So as a sort of thought experiment, I kind of thought, okay, look, if I take my energetic arguments and I kind of put them on these limits to growth charts, that sort of translates those very energy use, economy growth, very kind of abstract concepts into something a little bit more concrete that people can look at. So here's the space-based future, right? This is where Elon Musk gets his way. We start colonizing Mars. We start inhabiting the solar system. And we're on track for that, disassembling the solar system and building a Dyson sphere in the next 1,000 years. Cool. Modern medicine continues to get better. We need to populate the solar system. So you can see I've let the population just shoo, on the far left. The environment, well, it's great because I don't know if you saw the discovery of this huge asteroid recently. It's the sort of center of a planet that didn't quite form, and it's estimated to be worth $1,000 quadrillion because it's formed of such precious minerals that would take a lot of energy to mine out of the Earth here. Now, of course, if we can't retrieve the asteroid for less than $1,000 quadrillion, it's not worth anything, but fun thought experiment nonetheless. Anyway, resources in the solar system, we go and mine those. Well, we don't have to produce pollution on the Earth to do that. So the pollution curve goes down. I'm going to include CO2 in that. And the resources curve goes straight up. And, hand wave, okay, well, then that means something great for our economy. Now, again, as a physicist, there are some issues with this scenario. It is physically impossible to move a large fraction of our economy into space in a short time. We don't have enough rockets. If we did have enough rockets, we would be producing so much pollution and CO2 that it would defeat the purpose. And I'm hazarding that we're not going to see self-sustaining or indeed colonies with birth rates much larger than those on Earth anytime soon. So simply physically making this happen in the required timescale to combat our energy crunch. Impossible is a strong word, but I'm a physicist and I don't see it happening. So, steady state. Some of you brilliant people in the audience who are economists or ecologists or, you know, social psychologists, you figure out a way to disabuse us of this idea of infinite economic growth. And we maintain the parts of our civilization that we really need, like medicine and food. We abandon slowly or reprioritize the bits that perhaps we don't need, like hopefully defense. And so our birth rates level off, our death rate, you know, we keep the medicine, that's all good, and our population stabilizes. We start recycling in massive, massive scale. We transition thoroughly to renewables very quickly so that we can avoid the climate crisis, and we need to sequester the carbon. And so we transition into this sort of non-economic growth world. I love this. I want my kids to live there. I don't really want them to live on Mars. I want them to live in this reality. But I don't know how to make this happen. I have read a lot of economics, you know, popular economics books to try and understand how you get to this. And I don't understand how you get to this. So I'd love to hear more from you know, people who are thinking outside. But I think if we can tell the story that this is a world we could work toward, and indeed this is a world we have to work toward, that's an important step to take. And then this is the scenario that we don't want to talk about and we don't want to happen, which is exactly the scenario predicted by Limits to Growth, which is that we continue to escalate our pollution and deplete our resources, go through peak oil. We may well have gone past peak oil, but we don't transition in time to fix parts of the economy that depend on non-renewable resources, and we face a very large spike in death rate, and that eventually leads to a decline in population. These are not things that I want my kids to live through, but it looks to me like all we need to do to get to this future is nothing. And so that's why I'm giving this talk, because I'm not an expert on any of these areas, but I am very used to looking at complex systems and estimating how they're going to behave. So I think it's important that we consider these scenarios. And why do we find it so hard to consider these scenarios? Well, because we're humans. We don't like this bad news. I don't like reading articles about methane cloud rates. I don't like reading articles about the fact that the Arctic sea ice has not started forming for the first year ever this late. We don't really want to deal with this stuff. And if it looks abstract, if it looks just like a graph on a computer, we can quite easily say, I don't have to deal with this. I've got bills to pay and I've got things to do, which is true and difficult to deal with. So again, the psychologists among you might have some way of convincing people that we do need to do something. But as far as I've seen, a lot of people have been shouting very shrilly about this for very long time, and nobody's really willing to focus on the problem for more than a few minutes because it's so upsetting if you understand the graph. Otherwise you can just say, it's a graph. And the other thing is we have a sort of collective failure of imagination. Every time we talk about anything now, it is always framed with this capitalist framework. Everything is a business. Everything has to generate growth. One of the questions that John speculated I might be asked is, why should we fund astronomy? You know, why should we fund anything? What are we here to do? Is our society just here to make things as efficient as possible, to convert resources into waste as quickly as possible? Is that what we're here to do? What happened to art or beauty or exploration? What happened to helping each other and looking after each other? Why does everything have to be phrased in terms of profit? And I think it's that collective failure to imagine a different way, and the way that, even quite left-wing, quite green parties will talk about sustainable development as if it is a thing that can be done, that locks us in and stops us from, considering other realities. I mean, I think the biggest thing for me was you've got news articles saying we need to stop climate change. We need to cut our carbon emissions by approximately 10% every year for the next 50 years. And at the same time, you've got an article saying COVID has reduced our carbon emissions by 7 or 8%. Okay, great, because of the cessation of international air travel. But then the very next thing is every politician of every stripe saying we have to get the international aviation sector back on its feet so that we can keep our economies growing. So we are trapped in this loop as far as I can tell. So all I can do is just keep shouting and hope I don't lose my job or my funding because of it. So that's the doom and gloom. That's the astronomical perspective on this problem, which is, graph heavy. At least on our individual scale, we can always do something. And in our organizational and group scales, we can do something. So I'm very pleased that in the last year or two, astronomers have really not all, that's an overstatement, but many of us have really started to realize what a serious issue climate change, and some people are willing to admit as well that it's a symptom. So what are we doing? We're not just sitting here telling everybody that the world is going to end. What are we doing about it? Now, astronomy is a carbon intensive process. I cycle to work. I try not to eat too much meat. I reject unnecessary travel. However, I use great big radio telescopes powered mostly by coal power to observe the universe. I then perform computations on those data and using great big supercomputers, which again are not always powered by renewables. And then I fly all over the world presenting my work. And scientists, we're quite terrible. Scientists and academics generally, in terms of our carbon emissions, we are not shining examples for the rest of humanity. We are quite selfish because of the system we're in, where we need to do our jobs. So all of this is quite carbon intensive. So what can I do? Earlier this year, we had a series of papers come out in astronomy about reducing carbon emissions in astronomy. And this is what I was just saying. Astronomers, worse than Australians, who are worse than the global average. And breaking down those emissions that we were producing by doing those tasks into the different kind of things that we need to worry about the most. So supercomputing is absolutely this. I mean, I don't think most astronomers really even considered it, but it is absolutely terrible for the planet. It is just running great big farms of computers. Admittedly, there are, many other people using supercomputers, data centers. Every time you do a Google search or an email, you're using a computer somewhere. But still, astronomers are particularly bad. We do fly around, and our observatories and offices are generally powered by non-renewables, just like everyone else. So in order of the data coming through the system to me, what are we doing? Observing. Typically, when people think of astronomers, they think of us going off to a cool telescope, like in my first slide, and standing there or like listening. Has become decreasingly the way that things are done. And of course, with COVID, all observatory travel has been cancelled. So those last few observatories that weren't already using either remote or automated scheduling are having to transition rapidly. So with remote observing means that astronomers don't have to fly to the remote location and give their do their observations. And so, that decreases the carbon cost, which is good. There are also more and more observatories being powered by renewable energy. So the Murchison Radio Astronomy Observatory that I showed in the first slide has a huge solar farm, which is going to supply part of the SKA and is currently supplying the telescopes there. So we're doing as much as we can within the framework to try and make this stuff carbon neutral. Supercomputing, see, it's the big one. What are we doing? Well, pleasingly, the biggest supercomputer, Rygen, which runs in NCI, the National Compute Infrastructure in Canberra, because it's in Canberra, it's in the ACT. Because the ACT have a progressive state government, it's 100% renewable because the state government has sensible policies. Swinburne have done an extra effort to make their computer green. They have purchased a renewable energy contract inside Victoria to get their power supplied. It's kind of a trading scheme, so they say we give you this money and this much renewable power will be produced. Whether the actual electrons themselves are generated from that specific power plant, but it's good, right? It's money into the right sector. Here in WA, we are somewhat hamstrung by our very separate electricity grid, which has a sort of legacy of different state governments making different decisions. So unfortunately, we don't have very much in the way of renewables, and our supercomputers are polluting. I do take some heart from the fact that both the Pawsey Centre and Down Under Geoscience, the two biggest supercomputing centres in WA, are both worked quite hard to make them as efficient as possible. And they do have very good support structures to get researchers like me to write efficient code. So we're not just generating heat for no reason. But of course, a WA strategy toward renewables would mean that pretty much all astronomy or astronomical computing in Australia would become carbon neutral, which would be wonderful. So I'm interested in putting something together to propose to the state government. I've just got a bunch of talks to record for some conferences coming up. So if anybody has contacts or would like to talk to me about it, then that would be great. Now, conferences. This is a big one because a lot of people can't wait for these to resume again, but of course they are terrible. So this plot shows the American Society of Tropical Medicine and Hygiene 2019 conference, a sort of reasonably large academic conference of nearly 5,000 people. And these are all the trips from all of the different cities that all of the different participants took to go to one little corner of the northeastern of USA. And at the bottom, you can see it generated nearly 9,000 tons of carbon for that 5,000 people. Of course, if you add up all the flights, it's more, but for those people. And they experimented with a hub-style conference. So instead of having everybody fly to that one location, instead everybody flew to their local location or took the train if they could. And then those hubs were connected with very nice video conferencing systems. And you can see down there that they've therefore only spent 3,500 tons of CO2, which they point out is a factor of 2.5. Hooray! That's not really good enough. Sorry, everybody. I was a big fan of this model until I did the calculations. And yeah, it doesn't really help enough because we need to decarbonize by 10% every single year forever. A factor of 50% 1 year, but then you can't go any further with this. It's not very good. So, COVID's given us an opportunity. I was a co-organizer of a meeting called The Future of Meetings earlier this year. My Twitter recording is at the bottom left, and the kind of archive site where you can see all the talks is at the bottom right. And we literally had a meeting about how can we do inclusive, sustainable, accessible meetings that don't drive you nuts using all the different kinds of technology available. And it was a lot of fun. And this little screenshot here shows some of us using a platform called gather.io, where or gather.town, I think, where you log on and you have a little avatar and it has proximity sensitive audio and video. So you can have a poster session and the posters are all there and you can be reading a poster. And if somebody comes up to you, their audio and video fades in and you can start talking to each other, and it's very natural. There's this physicality to it where you can hear a hubbub of voices. You can see people moving to lunch. It joins us together in that kind of group feeling that I think is missing in a lot of virtual interactions, like this one where I can't actually see any of you. So this is a factor of 1,000 less carbon. This is considerably better for the planet. This is no worse than watching Netflix. So efficiency gains aren't going to get us everywhere, but if we want to maintain academia and want to maintain our research networks and not just shut it all down, solutions like this, I think, are part of the future. Now, finally, I've covered the sort of 3 things that astronomers produce carbon with and how we've kind of tried to fix them. But just in the very last part of my talk, I want to talk a little bit about what else we can do as astronomers. And, you know, this talk is an example. So we try and do a sort of outreach to people, and you know, often we're talking about the thrill of STEM and how people should get into STEM because it's so cool, and you know, we're often seen as like a gateway field because we've got beautiful pictures, but then all the difficult tensor calculus comes up when you least expect it. But I think that besides just raising people's awareness of science being cool and maybe getting kids into it, the energy arguments that I put forward earlier are also quite useful. There's this kind of big scale that we can get to. There's also people who do comparative planetology. That is a real field. So they look at the temperature of Venus, for instance, versus the temperature of Earth. They're both about the same size. They have very similar kind of geology, and yet Venus is a hell world of thousands of degrees Kelvin, and we have a nice, you know, water planet. And it's not just because of the distances to the sun. There's things to do with the rotation speed and the presence of sulfuric acid and so forth. So that sort of comparative planetology is super interesting, and there's some really good talks. I'll send you a link in a second about where you could have a look at some of those. We're also seen as quite independent people. So, you know, obviously people spend a lot of time trying not to listen to climate scientists and trying to say, oh, well, they're conflicted. They obviously want their field to survive. Everybody wants their field to survive. So I'm hoping that if I comment on things like climate science, I won't be seen as being part of big green or whatever conspiracy theory du jour there is. I am just a person doing the best I can to draw conclusions based on the facts that I can, as far as I can see them. Cosmic perspective, I guess I sort of hope that thinking a little bit about why are we here and what are we doing and why is it so important that we make a little bit more money in the third quarter gives people an idea that there's a lot more out there, and you know, maybe that's not the focus that we should have. And of course, finally, the fact that there's no planet B. So, you know, we are looking for other habitable planets, but even if there were one, we would not be able to move to it. That is a fantasy. So I think we are the best placed people to puncture those space cadet fantasies. The final thing is just this graph that I threw in yesterday, actually, which is another thing that astronomers can do, albeit a slightly depressing one. This sort of complicated graph, sorry about that. There's a red line on a y-axis against time. The y-axis is the CO2 concentration as measured by chemistry people who are like literally measuring how much CO2 there is in the air at a location on Easter Island. And that's the red line. It's going up. Surprise. The black line and dots are astronomical observations of a distant source, nothing to do with the Earth. And what we're seeing is there's so much CO2 in the atmosphere now that it's producing visible spectral lines in our observations. So we can actually see our own atmosphere in CO2, and we can measure that getting larger and larger and larger. And it's actually causing the rising temperatures are now causing problems for astronomers at different locations because we need cold and dry atmosphere in order to see through. So yeah, just thought I'd throw that in there as, you know, we do also care, and we can also make measurements, but I hope that doesn't stop us being unconflicted. So finally, I just thought I'd say there's now a group called Astronomers for Planet Earth, which I'm a part of. And we have a website, and you can go there and check it out. We have some lovely videos and things about our group and what we're trying to do, and some of the ways in which astronomy can, you know, reflect on the climate. I should really put a video up about the energy arguments, but I'd love to hear somebody punch holes in them first. I do have a short video, but John, I don't know if I have time. I don't have a timer on this. So I have a 3-minute video I could play. Do I have time?
Maybe. It's already 9 minutes to 5. Play a minute or so of it, and then remember.
Okay, I'll just play it very briefly, but I'll stop a bit in.
Hi.
Namaste. Bonjour.
Hola.
Hello.
Namaskar.
G'day.
We're a group of astronomers and we have an urgent message to share.
The world is on fire, literally.
The climate crisis.
Will only get worse if we don't stop burning fossil fuels.
If we don't stop,
Burning fossil fuel.
We are the first generation.
experience significant impacts of the climate crisis.
Possibly the last one that can still make a difference.
And the last one that can stop planet breakdown.
Can still stop.
Climate breakdown.
So I'll pause it there. If anybody else wants to see that video, you can hop onto the Astronomers for Planet Earth website. It's very sweet. Those are all real people that I have worked with in the past. So it's not just me, just, you know, shouting. There's lots of people who are concerned. And I'd also like to just, you know, reiterate, like just into her den here. We could do better, and it could be better for everybody. We don't have to see this as a problem that we solve, and therefore things, you know, we have to give up things. It's possible that with a bit of wealth redistribution and a change about what we concentrate on, you know, this could be a positive thing. So I think it's important that we keep bringing this up, understanding what our own perspective brings to the problem, and yeah, do our best to keep talking about it and not hide for the sake of our kids, if no one else. So thank you very much, and I'm happy to take questions.
Thanks very much. It's great. Just trying to see where I am. Here we go. Hi, everybody. Well, thanks very much. Just reminding you again, if you want to go into Slido to ask a few questions, we do have a few. Go to www.slido.com or download the app, and the number of our event is 2164. So thanks, Natasha. A lot to take into. You can unmute yourself now, by the way, because then we can just go back and forth with some Q&A.
Sure thing.
Lots of big Qs here, some of which are from me, but I'll try and find just a very quick one. I thought the Pawsey supercomputer used geothermal power over there.
They do to cool the building.
Ah.
So, yeah. I don't think that they use it to power the supercomputers, unfortunately. That's grid.
Right. Okay, fine. I knew there was I thought it was quite a big innovation to get the geothermal for the apartment.
Yeah, I think it's a heat pump, and so it's not like it's like a volcano or anything. It's just a heat pump to regulate the temperature of the building, and they have solar panels all across the top. But yeah, I did check with them. I had a chat.
Okay. Somebody just comments like a global change from GDP to a happiness index or similar, as adopted by New Zealand, and you had Jacinda Ardern up there.
Yeah.
The model of demographic transition to a stabilised, sustainable growth is one solution. So you didn't talk about population, and I know that the limits to growth certainly did talk about population. Have you done some modelling on population issues as well? So
I'm not an ecologist or an economist, and it's a very politically sensitive topic. So I certainly don't do my own modelling. I do read, and from what I have seen, the largest contribution to carbon emissions in the last 30 years has come by far from the top 10%, you know, of GDP countries. And yes, we should be concerned about China and India as they transition to being more developed and they have more people. However, both those countries have made strong commitments to actually going carbon neutral, closing their coal-fired power stations, and doing something, while our democratically elected leaders simply hand-wring. So I think it's tricky. And the other thing about population is, what are you going to do? You know, we're not going to like let the pandemic run loose. We're not going to forcibly sterilize people. People have rights. We should all consider every other person as if they could be our own or our own child. So the best, as always, the best possible thing we can do to reduce uncontrolled population growth and demand on the Earth's resources is empowerment for women, access to contraception, access to safe abortion, and, you know, family planning. These things are super important and obviously have had a huge impact in the past. So who you vote for and the kind of political campaigning you do, you know, all these issues are connected. And if you're fighting for women's rights, then you're also fighting for the environment.
Sure, that's good. I had asked my very first Dorothy Dixer just to get things rolling. In a sense, you talked about it a little bit, talk about what are astronomers doing on this whole issue. But I wondered, has there been any economic benefit analysis, or if you like, looking at environmental / economic trade-off analysis of big science projects like the SKA or the Murchison Array? Because I mean, one of the apart from its intrinsic scientific value, of course, it was also touted, we wanted to put money into this because it will have various spin-off benefits, i.e. Economic spin-off benefits, but they would have to be offset against potentially environmental and other downsides. But maybe it's also got some sort of environmental benefits too in terms of what it's exploring. So has in that astronomy sort of analysis you talked about, does anybody look at particular projects as opposed to the the conferences and the supercomputing itself?
Yes, so I'm not an expert, nor have I worked on that specific aspect, but right now, definitely, that is a big focus for observatories, including the SKA, is how can they power themselves via renewables? And that solar farm at the MRO, is concrete testament to the willpower to make it happen. For another reason, solar is just more reliable in the outback. I mean, using diesel, shipping diesel up to the MRO, that's how the very early prototyping was done, is not sensible or sustainable when you can just get the power straight out of the sky. So yes, absolutely. And in terms of the ecological impacts, like the footprint of the telescopes, all of the site infrastructure, every single part has had a heritage and environmental walkover to make sure that nothing of either cultural significance or environmental significance is being disturbed. And we have strong outreach and partnership programs with the communities that live in those areas to go and talk to them, answer their questions about space, and do all the good outreach that we do try and do. So we're trying to address those things in as much as we can within our little area. But I would sort of say, like, what's worse, a telescope or like an open cast mine? There might be bigger gains to be made by looking at, say, Adani.
Sure. Tim Diamond, hi Tim, a regular on our from Unions WA on our Curtin Corners, asked a question which I must admit I'm just trying to work out here. So are you saying that type 1, 2 and 3 civilizations on the Kardashev
yeah,
presuppose that intelligent life cannot limit its energy consumption?
Am I saying that type 1, 2 and 3 presuppose that we cannot?
Can you explain type 1, 2 and 3 civilizations?
Oh, sure, yeah. Okay, so Kardashev scale is a scale for fictional sound is too cruel. Potential or like possible civilizations, not necessarily alien, because this is a scale that we could get on, to talk about how they become kind of masters of the universe. I can't remember the exact scaling. So a 1 is, I think, they use the energy from their star, and like a 2 is they've expanded into space, and 3 is like a galaxy, something like that. Yeah, I'm not entirely sure what the question was. Are we saying we presuppose we cannot limit our energy use? Sorry, it's a little bit too convoluted for me. Do you think you can get at what he's saying?
He's saying, are you saying that type 1, 2 and 3 civilizations on that Kardashev scale presuppose intelligent life cannot limit its energy consumption? And your graph sort of showed, like, as you get over, you just go to 2%, bang, the power of compound interest, if you like, suddenly the whole of the galaxy.
Yeah, so I would say I've got 2 reflections on that question, possibly not answers. One is that if we suppose that evolution acts on other living organisms in the universe as it does on us, that it breeds creatures which want to acquire territory and make their environment more suitable to having more progeny. I think it's a bit hard for evolution to produce creatures which can think in the long term. We have to really, really get above our animal desires in order to do this suppression of economic growth. I kind of see capitalism as the sort of evolutionary imperative that we are just allowing ourselves to do. I want more stuff. I want a better house. I want to go further. We're just letting our genes talk, and that's disappointing. Whether other aliens maybe have a stronger ego or superego than their id, I don't know. That's completely speculation. The other thing I'd say is that you do have to limit your economic growth and your energy gain for certain parts of your development along that scale. You absolutely have to. The speed of light is not negotiable. So you can build a Dyson sphere, encapsulate your star. You've got to go off to another star system to do the next thing for another star. It's gonna take some time. And then when you get there, you've got to demolish that solar system, if you apparently don't care about other planets at all, and build another Dyson sphere. That's going to take some time. And so I think that, you know, this sort of selects for aliens that can cope with periods of growth, periods of stagnation, periods of growth. And of course, you've got to worry about the coordination problem. Why should I care if energy is being generated on Alpha Centauri for a civilization that is 30 years of contact away from me? Why is that in any way something that I include as part of my own civilization? It's completely separate from me. So I think that whole Kardashev math of interstellar civilizations just doesn't make sense from a coordination point of view. Very quickly, you just become completely different civilizations, and why should you care about continuing to expand?
Okay. I mean, it's sort of following on from this to some extent. I was asking this question about astronomy deals with such huge scale and concepts that actually, to most ordinary mortals, seem completely incredible and unfathomable. You know, it's like light years, millions of light years, galaxies.
Plotted on a log scale. It all comes, it's all fine.
You know what I mean? Basically, it seems
Sure.
unbelievably incredible, and people can't get their head around it often. But it's, I think nowadays, you'd say it's generally trusted. But why can't we then do the same when people like you do, provide energy or economic projections based on basically maths, do the maths, and we also, that can't be right. But we can say, but it's right about the black hole, about expanding universe. Sure. Oh well, yeah, fair enough. They're smart people. They know what they're talking about. But but when you then bring it down to earth and say, but of course, if we just use those sorts of tools that we use to try and model what we're currently doing, we say, oh, obviously they've made a mistake. It's
very hard to convince anybody of anything that their job depends on not believing, and I'm included in this. You know, I and a lot of other people who mention this kind of thing are putting our own careers at risk, right? By speaking up, and I definitely run the risk of being, called, you don't know what you're talking about. But that's why I've stuck to such basic arguments. This is very, very non-negotiable physics here. Energy in equals heat out. Percentage growth equals, exponential equals heat death of the earth. Like, there's very broad scale, there's no complexity, and it's a reductio absurdum that leads you to say something must happen before that breakpoint. So yeah, I think people just don't want to hear it because it's depressing, and certainly we are then asking ourselves, what do we do about it? And so that's why I end the talk by saying this is what astronomers are doing about it, and like my personal stuff that I'm doing about it is looking at local climate action, building resilient communities, of course all the personal environmental effects that I can have, and looking at reframing whenever we talk about things as what's the economic benefit, what's the financial benefit, asking the question, why do we have to frame it like that? Okay. Someone also asked about, we've sort of half answered this, about isn't improving incomes, i.e. from economic growth, responsible for declining birth rates? And I think you half answered that question by saying actually more importantly has been the education and empowerment of women, and but maybe there is well, certainly we have essentially at our fingertips, all of us, tens of thousands of energy slaves. So we can, at the touch of a button, call a pizza or, make a phone call to a distant part of the world. We have all this energy available. And for a long part of humanity, we didn't have that energy available. The people who did that work to make the food happen, to pick the harvests. You know, there's a lot of hidden work that was never written down, and a lot of it was done by women. And of course, all of it was done by very poor people. So yes, absolutely, economic growth has been responsible for lifting people out of the drudgery of doing kind of repeated agricultural work. And, you know, drudgery is all I can say for a large period of history. And I'm not wanting to throw away all the advances that we've made. I'm just pointing out that we are on track to throw them away by default. And it would be better to transition to a society where we can still retain things like food, medicine, video calls like this would be also great. Astronomy.
Good point. Bruce was asking about related to this issue of decoupling of energy growth from economic growth. What's the relative importance of changing the composition of GDP and technological change, which of course comes down to the classic IPAT equation: impact equals population times affluence, which is another euphemism for technology. Plus technology, affluence, the level of the standard of living you've got. So where in that equation, we've already talked about population, you've got level of, or standard of living and technological change. So, I mean, there's a lot of discussion that basically we need massive amounts of investment in technology to try and offset some of the understandable desires for increases in living standards.
So yes, and I guess I would try and draw a distinction between standard of living, you know, those things that we need to, get by, and, you know, you shouldn't be working 80-hour weeks to just barely have enough to eat and never have a hope of owning a house or, you know, somewhere safe for your kids to grow up. There's some level at which we really, I think, everybody deserves to live. And then there's kind of consumerism on top of that. And of course, consumerism is at the moment the engine that drives us to be able to have a standard of living. I'm not an economist, so if somebody could work out a way of decoupling these things, that would be wonderful. Because I think one of these things is important, and the other is something that culturally we can train ourselves out of, or at least I have to have the optimistic faith that we can train ourselves out of.
But in terms of the technological or sort of structure that delivers some of those goods and services, they can be changed. So you could assume you could still have a consumer society, but based around different technology.
I'm not sure it's a technological solution. I think, like I said about the cruise ships, right? If you consider a VR headset as a good replacement to a cruise ship experience, then maybe a technological substitution is possible. I'm saying more like, how about instead of putting on the VR headset, you go and have a game of cards with your friend, right?
I mean, that's a change in the composition of one's life as well as and hence the economy as a whole.
Yeah, and how do you get from here to there? That is a huge question. And I just think it's something that we should all be asking ourselves, and what we can bring with our perspective, because I can only bring my astronomy and the small aspects of my lifestyle that are applicable. There's so many people out there with training in all different fields. If we think about it as this problem of, well, we have to, or the earth melts, then what are we forced to come up with? What is that creativity that we get from that constraint?
I'll probably make this the last question from Peter, saying thank you, Natasha. It's not really a question so much. It's a fascinating presentation that challenges us all. Is there any material suited to primary school age kids, some of whom are drawn to astronomy? So I think more broadly about astronomy, but also there's other things that astronomers do.
I mean, okay, so I have a primary school age kid. I wouldn't torment them with this level. I'm really hoping that as adults we can have a more positive message to pass on to them. But I do think the Great Realization, if you've seen that video online, that's quite a beautiful child-friendly understanding of how the pandemic has made us rethink what's important to us. So that's quite a nice thing if you look that up. And in terms of books, yeah, my kid's a little bit young, so I'm not quite there yet. But you can drop me an email if you go to my website. You can ask me an email. Maybe we can come up with some ideas offline.
I mean, one thing that must be said is about astronomy. I mean, you mentioned Carl Sagan, but just that, you know, astronomy and space travel and space has had a massive impact culturally, I think, on environmentalism. I mean, it was the, you know, the blue dot or the pale blue dot, the picture of the Earth by the astronauts, by, was that Apollo 11, who filmed, you know, turned around and filmed.
Film
And,
the Earth, yeah.
I mean,
Yeah, and like from my life, the reason well, one of the reasons that I'm in astronomy is because I watched a lot of Star Trek, and in original Star Trek, like and TNG, rather than the current stuff, which is a lot more explosions, pictured a world which was post-scarcity, and diversity was encouraged and valued, and we learned to work together to accomplish common goals, which were not purely financial. So I didn't know, but it was very good, you know, rearing to eventually become an astronomer concerned about issues like this.
Anonymous for correcting me, it was Apollo 8, but yeah, it was like that photograph of the blue Earth. I mean, had a massive impact on people's environmental consciousness. Just as,
Sure.
I think, like I said, Sagan and other, you know, the realization of on one hand, how small we are in the universe, but at the same time, precious, because it seems to be the only place where there's, you know, life, like you said.
Yeah, and even in our own solar system, you know, there's. I know Musk wants to build colonies on Mars, but it's not. I mean, do you want to live in a submarine for the rest of your life? It's a radioactive submarine with low gravity, so you get osteoporosis, and you have to, you know, recycle all your own water. You never see a tree again. Yeah.
Okay, well, on that happy note, can I thank everybody? Thank you very much for attending, and you too, Natasha. Thank you so much for your presentation. Those the slides, the PowerPoint will be up on our website next week, plus the questions and answers and Natasha's talk. And once again, please get your colleagues and friends to look at our website and see some of the other talks we've had. Next week,